Alright, in this video we'll be going through the 2018 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. All elements emit a number of distinct wavelengths of light known as spectral lines that are unique to each element. Hydrogen emits 4 visible lines as shown below. Obviously there's no diagram because NCEA moved it for copyright reasons, but I'll put up an image of what it should look like. Light from a hydrogen source can be passed through a diffraction grating to form an interference pattern. The wavelength of each spectral line can be determined by measuring the angle to its first order maximum. The lines on a diffraction grating are spaced 1.68 times 10 to the 6 meters apart, show that the wavelength of the spectral line with the first order maximum at 16.8 degrees is 4.86 nanometers. Alright, so we know that our n lambda is equal to d sine theta. Okay, we're given our d value right here. We're measuring the angle to its first order maximum, and therefore n is equal to 1. And so therefore we can simplify this equation and say that our wavelength is equal to d sine theta. Okay, and we are given our angle, so we can now simply plug in our numbers. We get our wavelength is equal to 1.68 times 10 to the negative 6 times sine 16.8 degrees. And this gives a wavelength of 4.8557 times 10 to the negative 7 meters. And that indeed can be simplified to 486 nanometers. There we go. The telescope is rotated from the 16.8 degree position to position Z, which is the location of the next spectral line. State the wavelength of this line and explain your reasoning. Alright, so this question is impossible without the image that we are not given. Alright, so we need this image. So I'm gonna put this image roughly right here. If you look at that image, you can see that our 486 nanometer line is our green line, okay? That's our green line. If we go to our diagram over here, if we are moving it from the 16.8 degree position to the Z position, we are increasing the angle, okay? So our theta value is increasing, and therefore as n lambda is equal to d sine theta, if our theta value is increasing, therefore our wavelength must increase, okay? And if we look at our image again, we should see a red band on the right hand side, and that wavelength should be 656 nanometers. Alright, so this is our final answer of the wavelength of the next spectral line. Calculate the maximum number of orders visible for the 656 nanometer line. Alright, again, our n lambda is equal to d sine theta. In order to calculate the maximum number of orders visible, we can set our theta to 90 degrees, okay? Alright, and the reason why we do that is because if we have our screen over here and we're shining light through our diffraction grating, obviously the light isn't going to come through here and then go backwards, okay? So the maximum angle from our first order maxima is 90 degrees, okay? And let's say just for example, we have 3 orders of maxima. That means we're going to have 1, 2, and then 3, okay? So our third order maxima is going to be less than 90 degrees. However, our fourth order maxima is going to be greater than 90 degrees. So that's why we set it to 90 degrees, so we can get all the maxima that are contained within this region. So now carrying on with our calculation, we can rearrange for n, and we get n is equal to d sine theta all over our wavelength. Now plugging in our numbers, we get 1.68 times 10 to the negative 6 multiplied by sine 90 degrees. Now we should know that sine 90 degrees is equal to 1, okay? So if we want, we can just get rid of this from the calculation. And we divide that by our wavelength, and we get 656 times 10 to the negative 9 in order to convert it into meters. And we get our n value as 2.56, and therefore our highest order is 2. Okay, now it's a common mistake to say that we get 2 more orders of maxima on either side, and so therefore we have our central maxima and 2 orders of maxima on either side, and therefore our max order is 5. This is incorrect because we are not asked for the maximum number of maxima visible, we are asked for the highest order. And the highest order is just the amount of maxima that are on each side of the central maxima, okay? So in this case, as you can see, it's 2. Like we calculate. The diffraction grating is replaced with a double slit that has a slit separation of 1.68 times 10 to the 6 meters. Describe and explain any changes that will occur to the location, brightness, and width of the maxima for the 656 nanometer line. So this is our classic question. However, this time there is a slight twist. Because our d value this time is the same for both the diffraction grating and the double slit, the maxima will be located at the exact same location. Okay, so usually when we convert from a diffraction grating to a double slit, we say our d value has increased and therefore our maxima are closer together. However, in this case, we cannot say that okay? Because again, the slit separation for both the diffraction grating and the double slit are the exact same. And so the angle of the maxima are going to be the same, so our theta value is going to be the same. And so therefore our maxima are going to appear at the exact same location on the screen. Okay. However, what will change is the brightness, okay? For our double slit, the maxima will be dimmer. The reason for this is because when light diffracts, either through a diffraction grating or a double slit, the propagating waves that come out of that double slit or diffraction grating act as point sources, okay? And so therefore, as a diffraction grating has much more slits than a double slit, therefore effectively there's going to be more sources of light, and therefore when those lights constructively interfere, there's going to be more waves constructively interfering, and therefore the bright spot is going to be brighter. Okay. As for the width of the maxima for the double slit is going to be wider compared to that of the diffraction grating. The reason for that again is because our diffraction grating has much more sources compared to our double slit, and therefore there's going to be less destructive interference for our double slit when compared to our diffraction grating. And what this means is that for our double slit, our maxima are less defined, and therefore there's going to be more light. And if you want to visualize that, you can either look it up on Google, or in my second part of my interference videos on my Waves playlist, is towards the end, I go through comparing the diffraction grating to a double slit, and you can see the width of the maxima being different. A bull roarer is a carved piece of wood attached to a string. It can be strung around the head to create sounds that travel long distances and fluctuate in pitch. The user can control the changes in pitch by swinging the bull roarer around in a circle at different speeds. The bull roarer emits a note of 2 × 10⁻² Hz, as Joseph swings it in a circle with a period of 1 second and a speed of 6.28 seconds. Joseph is at the center of the circle. Describe the changes in sound that would be heard by a distant observer as the bull roarer moves around in a circle. Alright, so if the bull roarer is here, its velocity is going to be directly away from the observer. And so due to our Doppler effect, the observer is going to hear a decrease in frequency. Okay. Now, if the bull roarer is here, the velocity is neither going to be towards or away. It's at right angles to the observer. And so at this point, they're going to hear the true frequency. If the bull roarer is over here, the bull roarer's velocity is going to be directly towards the observer. And so therefore, this observer is going to hear an increase in frequency. And again, if the bull roarer is over here, the velocity is again neither towards or away from the observer, and so they're going to hear the true frequency. And as you can see, we go from true frequency to decrease to true frequency to increase, and we can actually graph this frequency over here, and we can have our time over here. We start at our true frequency, so we can start at our true frequency right here. We go to a lower frequency over here, then we go back to the true, and then we go to a high frequency, and then back to the true, like so. And as you can see, we follow a sort of a sine curve. And obviously this is just going to continue on and on and on. And as you can see, the observer is going to hear alternating high and low pitches, okay? When the bull roarer is at position shown in figure 8 on page 4, calculate the wavelength of the sound waves that Joseph will hear. So let's rub all this out, like so. All right. When the bull roarer is at this position, as this bull roarer moves around Joseph, it stays at a constant radius. And so Joseph will hear the true frequency the entire time. And so therefore we can just simply use our V is equal to F lambda, and therefore our lambda is equal to V all over F, and therefore plugging in our numbers, we know the speed of sound is 344 meters per second as it's given up here. And this is all over the frequency of 200 Hertz. And this gives a wavelength of 1.72 meters. There we go. Explain why the sound waves observed by the distant observer will not have the same wavelength that Joseph experiences. Alright, so if we have our situation here, we have Joseph over here, and this is our bull roarer, and this is our observer over here. In this scenario, the bull roarer has a tangential velocity in this direction, okay? So therefore, as the bull roarer moves this way, it's going to catch up to its previously emitted wavefronts. And then as you can see, the wavefronts in front of it are bunched up, but more importantly, the wavefronts behind it are spread out. And so therefore, these are the wavelengths that are going to reach our observer, and therefore our observer is going to observe greater wavelengths compared to the source. So that is when the bull roarer is in this position. However, when the bull roarer is in this position right here, it's going to be the flipped scenario. Okay, our bull roarer now has a tangential velocity in this direction, and so it's going to again catch up to previously emitted wavefronts, like so. And now just like in this scenario, the bull roarer has compressed wavelengths in front of it. And so now when the bull roarer is in this position, our observer is going to observe shorter wavelengths compared to the source. Now, Joseph does not perceive these changes in wavelength because the ball roller neither moves towards him or away from him. It stays at the same relative distance as it goes around his head, okay? And so because of this, Joseph will perceive a constant wavelength. Now, also one thing to point out, when I say you're perceiving a change in wavelength, you can't actually perceive a change in wavelength. A wavelength isn't something you can see with your own eyes, unless it's like a wavelength on a string, okay? But we're talking about sound, you can't perceive wavelengths of sound. And so perceiving a higher or lower wavelength really just means that you're perceiving either a lower frequency or a higher frequency, all right, respectively, okay? So when we perceive a higher wavelength, you're perceiving a lower frequency, which you can hear as a lower pitch. And if you're perceiving a lower wavelength, you're perceiving a higher frequency, which you can hear as an increase in pitch, okay? Just to clear up any misunderstandings. Clearly mark on the diagram figure A the two positions of the ball roller at which the distant observer will measure the same frequency as Joseph, and explain why the frequencies at this point is the same as what Joseph would measure. All right, so if we go all the way back up to our image, it's going to be this position here and this position right here, okay? And if we were just to draw out our situation again, okay? It's going to be this position and this position. When the ball roller is in this position, it's going to move it this way, and when the ball roller is in this position, it's going to move this way, okay? And as you can see, when the ball roller is in these two positions, none of their velocity component is in the direction of our observer, okay? And so, therefore, the ball roller is neither moving towards or away from the observer, just like Joseph, and so, therefore, they're going to hear the same sound as Joseph, as there is no Doppler effect being observed. Calculate the maximum and minimum frequencies that a distant observer will measure during one revolution of the ball roller. Use these to draw a graph of the variation of frequency against time starting from the position shown in figure A on page 4. So if we bring over our diagram, alright, we're starting in this position right here, and this is when our ball roller is moving in this direction like so. Now at this position, we are moving away from our observer, therefore we're going to use this Doppler equation. Right, we're using the plus again because we're moving away from our observer, and therefore now we can just plug in our numbers, and we get the source velocity, which is 200 hertz, times the wave speed, which is 344 meters per second, all over 344 meters per second, plus the velocity of our source, and that is given way up over here as 6.28 meters per second. 6.28 meters per second. There we go. And this gives a perceived frequency of 196.4 hertz. Okay, now when we are moving towards the observer, okay, remember that is when the ball roller is in this position right here, okay, we use this Doppler equation, right, we're using a minus again because we're moving towards the observer. Now plugging in our numbers, 200 times 344, all over 344 minus 6.28 meters per second, and this gives a perceived frequency of 203.7 hertz. Now, once again, when the ball roller is in these positions right here, no component of our velocities are in the direction of the observer, and therefore at these points we observe the true frequency of 200 hertz, okay? And so now we can graph this. Again, we're starting at this position right here, and so we start at 196 hertz. So we start roughly over here, right? That's 196 hertz. And then we move to the true frequency, which is right over here. Remember, this is after 0.25 seconds, all right? Because remember, it says up here that one period is 1 second, okay? And so therefore, as we are splitting this up into 4 sections, 1 divided by 4 is 0.25, and so we put a mark every 0.25 seconds. And then we go to this position right here, which we established is 204 hertz-ish, okay? And that's roughly over here. And then we go back to the mean right over here. Again, this is 0.5 seconds, and therefore this is 0.75 seconds. Like so. And then once again, we reach our starting position at 96 hertz, like so. And as you can see, we follow sort of a cos graph, like that. There we go. Clara wants to investigate the properties of a 0.4 meter length of a steel rod. The bar is clamped rigidly at the center, and the ends are free to vibrate. The rod is struck in such a way as to produce a fundamental longitudinal standing wave. Show the wavelength of the wave is 0.8 meters. A diagram should be included in your answer. Alright, so now if we think about this, if we are clamped in the middle, therefore the steel rod is unable to vibrate in this middle position, and therefore we're going to have a node over here. However, as our ends are free to vibrate, we're going to have antinodes on each side. And so we can model this as an open-ended pipe, where we have a node in the middle and antinodes on either side. And therefore we know the fundamental frequency of an open-ended pipe. looks like so. And we know the length is equal to 1/2 of the wavelength. And so therefore 2 times the length is equal to our wavelength, where our length is 0.4 meters. And so therefore 2 times 0.4 meters is equal to our wavelength, and indeed we get 0.8 meters as our wavelength, as it asks us to find. One end of the steel rod is attached to a diaphragm that can move freely inside a clear plastic tube. The clear plastic tube is closed at the opposite end. On the bottom of the clear plastic tube is a fine white powder. When the rod is struck, the white powder forms into ridges that are half a wavelength apart. The steel rod still vibrates at the fundamental frequency. The frequency of vibrations in the air in the tube is the same as the frequency of vibrations in the steel rod. Explain why this is true for the frequency, but not for the wavelength of the two vibrations. Alright, so Clara strikes the steel rod, okay, which then vibrates this diaphragm and therefore vibrating the air inside the tube. So because the rod and the diaphragm are attached like this, the frequency of both the rod and the air within the plastic tube is going to be the same, because the rate at which the rod is excited directly determines the rate at which this diaphragm and therefore the air inside the tube is excited, okay? So that's why the frequency is the same. However, the wavelength is different because of the difference between the wave speed within the steel rod versus the air inside the tube. The wave speed within the steel rod is faster compared to the wave speed of air within the tube. And so obviously we can go through this using two approaches. Our first approach is using V is equal to F lambda, and therefore saying as our frequency is the same in both cases, but our wave speed is different and therefore our wavelength must be different, okay? However, maybe a more intuitive way that will gather more understanding is that the wavelength is determined by how far a wavefront or a vibration is able to move away from the source before another vibration is made, okay? So let's visualize that. Let's say we have our source right here, and we produce a wave, okay? And so this wavefront is going to move outwards, and then after some time, let's call it time t, this wave is going to move out here, okay? So now the wave is over there. Then, after time t, we make another wave, okay? And this distance right here is our wavelength. Now, the distance that this wave travels before a new wave is created is obviously determined by our equation velocity is distance over time, where our time is time t, which is just an arbitrary time. However, our distance is our wavelength. So the velocity of the wave is equal to the wavelength all over the time, okay? Now, also just a side tangent, we know that this time is equal to 1 period because this is the time between each wavefront being emitted, okay? So this is equal to our period. And we also know that our period is equal to 1 over our frequency. And so therefore the velocity is equal to our wavelength all over our period, and therefore subbing this into here, we get our velocity is equal to our wavelength divided by 1 over our frequency, and therefore our velocity is equal to the wavelength multiplied by our frequency over 1, and therefore the velocity of the wave is equal to F lambda. Okay, so that's just how this equation gets derived. And so as you can see, from this intuitive explanation, we get our wave equation that we use to explain our first explanation, okay? So the first explanation is valid. You can do it in the exam. I'm sure that will give you the mark. However, this explanation shows better understanding, okay? So again, just to reiterate, as our rod has a higher v, velocity of the wave, therefore this wavelength, this distance is going to be shorter than in air. Okay, all right, because again, our frequency is the same, and therefore we're going to have the same period because our period is equal to 1 over the frequency, okay? And so therefore the wavelength in our steel rod is going to be shorter compared to that of the air in the tube. Clara measures the ridges to be 2.3 times 10 to the negative 2 meters apart. Calculate the speed of sound in the rod. All right, so it's given up here that the ridges are half a wavelength apart. And so therefore, if our ridges are 2.3 times 10 to the negative 2 meters apart, but our ridges are also equal to half a wavelength. Therefore, 2 times 2.3 times 10 to the negative 2 is equal to our wavelength. And therefore, this gives a wavelength of 0.046 meters. Now, as we established, the frequency within our steel rod is equal to the frequency of air within the tube, okay? And so therefore, as this is the wavelength of air within the tube, and we know the velocity of a wave in air is 344 meters per second, we can use v is equal to f lambda, and therefore f is equal to v all over our lambda, to find the frequency of air within the tube. And we get 344 all over 0.046, and this gives a frequency of 7,478.26 hertz, okay? And so therefore the frequency within our steel rod is also equal to 7,478.26 hertz. Again, as V is equal to F lambda, we just found our frequency and we calculated our lambda all the way in the first question, 0.8 meters. And so now we can just simply plug in our numbers, 7,478.26 times 0.8, and this gives a velocity of 5,982.6 meters per second. There we go. The clamp stand is adjusted and the steel rod is struck in such a way as to produce a standing wave of the second harmonic in the rod. Explain the effect this will have of the air inside the tube. Alright, so we know that our rod can be modeled as an open-ended pipe, okay? Like so. And therefore the second harmonic is going to look like this. Alright, and we would produce a standing wave like so, where our length is equal to the wavelength, okay? So previously, when we were producing the first harmonic, our length was equal to half a wavelength, okay? And so therefore 2 times our length was equal to the wavelength. However, now the wavelength is just equal to the length. And so we have decreased the wavelength. And so therefore as V is equal to F lambda, as the velocity of the wave in the rod has not changed, our frequency is going to increase. Okay? More specifically, we're going to have double the frequency, okay? The reason for this is because we have halved our wavelength, all right? And as F is equal to V all over lambda, if we have halved our lambda, we're going to have to double our frequency, okay? In order to keep the velocity of the wave the same. So we have doubled our frequency, and we know that the frequency of the rod causes the same frequency within the tube. However, as we look in our diagram, we can see that our tube can be modeled as an open and closed-ended pipe, okay? So our rod is an open-ended pipe, but our tube is a closed and open-ended pipe. Originally, we produced the first harmonic of our tube, which again can be modeled as an open and closed-ended pipe. However, as stated before, we doubled the frequency within the steel rod, and we found that the steel rod and the air within the tube had the exact same frequency, and so therefore the frequency of the air within the tube also doubles. However, this is an open and closed-ended pipe. And we know for open and closed-ended pipes, we can only have odd multiples of 1/4 wavelengths. And so what this is going to do is produce an even harmonic. But we know that this open and closed-ended pipe cannot resonate at even harmonics. We can only resonate at odd multiples of 1/4 wavelengths. And so therefore, no standing wave will form in the tube. All right, and with that, we're done. See it.